A modern sidewalk cracks after just a few winters. The dome of the Roman Pantheon has stood for nearly 2,000 years. This video reveals the 20 ancient material mixtures that created this impossible durability. You will gain a new understanding of human ingenuity, seeing the past as a masterclass in engineering we are still struggling to match. How did a bowl of sticky rice help hold the Great Wall together? What volcanic secret allowed Roman concrete to heal itself in seawater? We will uncover the hidden alchemy in stones, metals, and even tree sap that built civilizations meant to last forever. What does true resilience look like to you? That seamless dome of the Pantheon is a silent rebuke to our own crumbling infrastructure. It represents a foundational mystery in the history of building. How could mixtures of simple earth, ash, and stone achieve what our precisely formulated, laboratory-tested materials often cannot? The answer lies not in a single secret ingredient, but in a forgotten philosophy of construction. Ancient builders did not have the periodic table or electron microscopes. They had something else, a profound intimacy with the materials their land provided. They worked through relentless trial and observation, noticing that certain sands from volcanic regions made mortar set underwater, or that adding specific clays made a wall resist fire. This was engineering by feel, by result, and by generations of passed-down wisdom. They were masters of the how, creating mixtures that performed feats they could not possibly explain. Modern science now gives us the language for their genius. We call it pozzolanic chemistry, where silica-rich ash reacts with lime and water to form a rock-like glue that grows stronger for centuries. We identify it as accidental nanotechnology, where particles so fine they interact on a molecular level create incredibly dense, durable matrices. These long-term chemical processes, once set in motion, meant the structure was never truly finished. It was always slowly transforming, self-healing, and fortifying itself against time. So as we explore these 20 mixtures, we are not just looking at recipes. We are deciphering a lost art of collaboration with the very elements of the earth, and it all begins with the most iconic ancient binder of them all, a material that built empires from the ground up. That profound collaboration with the elements finds its most perfect expression in the dust of a volcano. Roman engineers discovered that a specific ash, a fine gray powder from regions like Pozzuoli near Mount Vesuvius, possessed a transformative power. They called it pozzolana, and it was the heart of their concrete, a material so advanced its full chemistry is only now being understood. The standard recipe was deceptively simple: lime, volcanic ash, aggregate like rock or brick fragments, and water. But when mixed and poured, especially in a maritime environment, something miraculous happened. While our modern concrete begins to break down in salt water, Roman concrete did the opposite. It grew stronger. The secret was a long-term chemical conversation. Seawater, percolating through the concrete, reacted with the lime and the fine volcanic ash. This slow, centuries-long process formed rare, plate-like crystals of a mineral called aluminous tobermorite. These crystals interlocked, creating a dense, incredibly resilient matrix that actually filled its own tiny cracks, a genuine self-healing material. We see this engineering masterpiece in action at the harbor of Caesarea, built by Herod the Great. Constructed in the open sea, this massive breakwater was made by lowering wooden forms and filling them with this volcanic concrete mixture. The seawater wasn't a threat, it was a crucial ingredient in the curing process. 2,000 years later, those submerged blocks are not just intact, they are tougher than the day they were poured, having silently fortified themselves against every storm. This wasn't just a better building material, it was a strategic revolution. With pozzolana concrete, Rome could build deep water ports anywhere, creating an unbreakable logistical chain that supplied its legions and connected its empire. It proved that true durability isn't about resisting nature's forces, but about intelligently inviting them into the structure, turning the chaotic energy of a volcano and the corrosive power of the sea into the very bonds of eternity. While Roman engineers harnessed volcanic fire, master builders half a world away found resilience in the bounty of their harvest. Centuries later, during the monumental effort to rebuild the Great Wall under the Ming Dynasty, laborers prepared a mortar that seemed more like a culinary recipe than a construction material. Alongside the usual lime and sand, they stirred in large quantities of a thick, glutinous soup made from boiled sticky rice. This was not a desperate substitution. It was a deliberate, ingenious innovation born from a deep understanding of their own agricultural landscape. The key component in that rice soup is a complex carbohydrate called amylopectin. When mixed into the lime mortar, this organic compound performed a subtle but powerful magic. It acted as a natural biopolymer, a kind of organic glue that controlled the chemistry of the hardening process. As the lime reacted to form calcium carbonate, the traditional binder in mortar, the sticky rice amylopectin inhibited the growth of large, weak crystals. Instead, it encouraged the formation of a much denser, more compact and interlocked microstructure. Think of it as the difference between a pile of loose gravel and a solid, fused block of stone. The rice made the mortar block like on a microscopic level. The practical benefits were profound. This biocomposite material gained significantly improved mechanical strength, becoming more resistant to compression and shear forces from the massive weight of the wall itself. It also developed exceptional water resistance, as the dense microstructure left fewer pores for moisture to seep into and expand during freezing cycles. The result was a mortar that was not just an adhesive, but an integral, reinforcing component of the wall's structure. Here, the line between the granary and the fortress completely blurred. This mixture represents a breathtaking fusion of domestic knowledge and imperial ambition, where the everyday staple that fed a population also became the literal glue that held its defenses together. It shows a philosophy where durability was sourced from the cultivated earth, proving that the ingredients for eternity could sometimes be found simmering in a simple kitchen pot. The blue-green shimmer on an Egyptian pharaoh's death mask was not painted on, nor was it carved from a single precious stone. It was something far more ingenious, a manufactured brilliance known as faience. Long before the invention of glass, ancient Egyptian artisans perfected this sintered quartz ceramic, creating a material that seemed to capture the very essence of light and water. To produce it, they began by finely crushing pure quartz or desert sand. This silica base was then mixed with two key ingredients, natron, a naturally occurring alkali salt harvested from dry lake beds, and a small amount of lime. The magic of the color came from a copper mineral like malachite added to the blend. When this damp paste was molded into a scarab, a tile, or a divine figurine and placed in a kiln, a silent alchemy took place. As it fired, the natron acted as a flux, migrating to the surface with the copper. There, at a precise temperature, the outer layer underwent a process called vitrification. The particles didn't fully melt, but they sintered, fusing together into a hard, glossy, glass-like glaze that was chemically bonded to the quartz body beneath. This created a brilliantly colored, incredibly durable veneer that was resistant to chipping and fading. The iconic turquoise blue hue was no accident. It was deliberately engineered to mimic the semi-precious stones like turquoise and lapis lazuli, materials associated with the heavens and the life-giving waters of the Nile. In objects like the golden mask of Tutankhamun, the faience was not mere ornamentation. It was a symbolic skin representing rebirth and eternal life, a bridge between the earthly and the divine crafted from common sand and salt. This mixture represents a monumental leap in material science, a non-clay ceramic achieving both dazzling beauty and structural integrity through a meticulously controlled chemical reaction. It was alchemy in the truest sense, transforming the mundane ingredients of the desert into a substance that glowed with celestial meaning, proving that durability could be woven from light and symbol as much as from physical strength. The same philosophy of working with nature, not against it, echoes from the dense jungles of Mesoamerica. Here, the Maya built cities of luminous white that pierced the emerald canopy, their temples and palaces covered in a brilliant plaster known as stucco. This was far more than a simple whitewash. It was a breathable skin engineered for one of the most challenging environments on Earth. The recipe began with lime, produced by burning limestone in carefully controlled kilns. But the Maya employed a lower temperature calcination process than their Mediterranean counterparts, resulting in a lime with a different chemical personality. To this base, they added a secret ingredient, organic extracts from the bark of local trees like the chukum or the habin. When mixed with water, this created a workable paste with almost magical properties. The tree sap acted as a natural plasticizer, making the plaster more flexible and easier to apply in the intricate reliefs and murals that adorned their buildings. More importantly, it functioned as a water repellent. Yet, the true genius was in the final product structure. This unique mixture, when cured, created a plaster that was intentionally somewhat porous. In the stifling humidity of the rainforest, this was a feature, not a flaw. This microporosity allowed the plaster to breathe, letting internal moisture vapor escape while the sap's repellent nature shed liquid rainwater. This prevented the trapped moisture that would otherwise build up, freeze-thaw cycles being irrelevant here, and cause the plaster to blister, crack, and spoil off in great chunks. It created a stable, durable canvas that protected the vibrant mineral and plant-based paints applied over it. The famous murals at Bonampak, with their stunning depictions of courtly life and ceremony, survived for centuries under this protective, breathable shell. This mixture represents a profound technological adaptation. The Maya didn't just build to impress, they engineered for permanence in a specific place. Their plaster was a climate-responsive technology, a testament to an ancient understanding of environmental harmony. It was the durable, breathing skin that allowed their art and architecture to withstand the relentless embrace of the jungle itself. Those brilliant white Maya walls stood as a testament to working with a specific environment. Yet another ancient approach to durability emerged from a more universal human activity, the simple act of breaking apart. In the civic heart of ancient Athens, the agora, if you look closely at the mortar holding ancient cisterns together, you'll see a mosaic of tiny, colorful fragments. These are not precious stones but crushed pottery known as koxiopsto. This was not a sign of poverty or haste, but a stroke of engineering genius born from urban necessity. In a dense city, broken ceramics were a constant byproduct of daily life. Instead of discarding them, Greek and later Roman builders gathered these fired clay shards, crushed them into coarse grains, and mixed them directly into their lime mortar. The result was a material transformation. The pottery fragments, having already been hardened by fire in a kiln, were incredibly stable and porous. This porosity was the key. It gave the wet lime paste countless microscopic nooks and crannies to seep into and grip, creating a far stronger mechanical bond than with smooth sand alone. But the magic went deeper. The clay in the pottery is rich in silica and alumina. When mixed with lime and water, these components slowly undergo a pozzolanic reaction, similar to volcanic ash, forming additional stable compounds that strengthen over decades. This created a hydraulic mortar, one that could set and remain durable even when constantly submerged. You can see its legacy in the intricate linings of Roman bath complexes. the vast underground cisterns that stored a city's water supply, and the channels of aqueducts where constant flow was a necessity. This practice represents one of history's clearest examples of a circular economy. It turned a waste product into a high-performance building material, solving a disposal problem while enhancing civic infrastructure. Every colorful speck in that mortar tells a story of a meal finished, an amphora transported, a household item that served its purpose and was then reborn as part of the city's very bones. It was durability crafted not from rare resources, but from the intelligent reuse of the ordinary, proving that sometimes strength is built from what a society chooses not to throw away. The silent resilience of a broken pot reborn as mortar finds its metallic counterpart in a single, soaring column in Delhi. There, standing over 23 feet tall, is an artifact that seems to defy the laws of physics, the iron pillar of Quartz. Forged in the 4th century, this massive 7-ton monument of pure iron shows no significant rust after more than 1,600 years. In a world where iron is synonymous with corrosion, this pillar stands as a quiet, impossible question. Its secret is not a magical coating or a sheltered location, but the very recipe of the metal itself. Ancient Indian metallurgists, through a process of direct reduction in a bloomery furnace, created an iron alloy with a remarkable and deliberate impurity, a high phosphorus content. This was not a mistake, but likely a result of the specific iron ores and charcoal used. The phosphorus, combined with the skilled forge welding of large iron discs, created a unique microstructure. Over centuries, this high phosphorus iron interacted with the environment in a benevolent way. A thin, stable film formed on its surface, a protective layer of a compound called Mosaics. This film is passive and adherent, meaning it clings tightly to the metal and actually prevents the underlying iron from reacting with oxygen and moisture. It is a self-maintaining shield, a rust-proof skin grown from within the metal's own chemistry. Modern steel, engineered for purity and strength, often lacks this protective impurity, making it paradoxically more vulnerable to the elements over vast timescales. The pillar poses a profound challenge to our assumptions. It suggests that ancient smiths working without modern chemistry may have understood durability on an intuitive, practical level we are still deciphering. They created not just a monument, but a material that entered into a long-term truce with the atmosphere, a testament to the idea that sometimes the key to defying nature is not to purify a substance, but to understand the perfect, durable harmony of its imperfections. That pillar's silent defiance of rust speaks to a mastery of earthly elements, but other ancient artisans sought to capture something more ethereal, light itself. In the great church of Hagia Sophia, the golden mosaics do not merely reflect light, they seem to generate it from within, a divine glow that has bathed the interior for over 1,500 years. This eternal radiance is not just an artistic triumph, it is a material one, achieved through one of history's most durable glass mixtures. Byzantine craftsmen were not simply making colored glass, they were engineering tiny, immortal windows. Their recipe began with pure silica sand, melted with a flux of soda ash from plant ashes and a stabilizer of lime. This created a stable glass base. But the true alchemy came with the addition of metallic oxides, copper for brilliant greens and blues, cobalt for deep sapphire, manganese for regal purple, and for the most sacred gold, a breathtaking technique. They would blow a glass bubble, apply a wafer-thin sheet of real gold leaf, and then blow another layer of clear glass over it, sandwiching the gold inside. This molten sandwich was then rolled into flat sheets. Once cooled, these sheets were cut by hand into thousands of tiny cubes called tesserae. The precision of the mixture and the firing temperature was everything. Too much soda and the glass would be unstable and prone to dissolving. Too little lime and it would be brittle and susceptible to cracking from temperature changes. The Byzantine formula achieved a perfect equilibrium, creating a glass that was dense, chemically inert, and resistant to the moisture, atmospheric pollution, and slight shifts of the massive structure around it. Each tessera became a microscopic fortress for its color or its captive gold. This is why the faces of saints and emperors, the scenes of biblical narrative, have not faded into ghosts on the walls. The stories they tell are locked into a material designed for eternity. In that dim, vast space, every shimmer is a testament to a forgotten science of permanence, where artists and chemists collaborated to ensure that the most fragile human concepts, faith and story and light, would be granted the most durable physical form imaginable. While Byzantine glass captured celestial light, a different kind of alchemy was at work in the absolute darkness beneath the desert. To bring life to the surface, Persian engineers first had to conquer the underworld. Their masterpieces were not soaring domes but inverted mountains, the qanats. These were hand-dug subterranean aqueducts, sometimes stretching for 40 miles, that gently sloped from a water-bearing aquifer in the foothills down to a parched city or fertile field. The engineering challenge was monumental: how to line these narrow, deep tunnels with a material that wouldn't dissolve under constant water flow or crumble under the weight of the earth. Their answer was a specialized mortar known as sarouj. This was a hydraulic mixture of lime, sand, clay, and often ash, but its true character was defined by its environment and its unique additives. Builders would sometimes enrich the blend with organic fibers like animal hair or even egg whites. These weren't mere thickeners, they were micro-reinforcements. The hair and egg proteins acted as a natural mesh, providing tensile strength to a material that was inherently strong in compression but weak in flex. As the wet mortar was applied to the tunnel walls in that cool, perpetually damp darkness, it began a slow, steady cure. The constant moisture was not an enemy here, but a necessary partner, allowing the pozzolanic reactions between the lime and the ash or clay to continue indefinitely, forming a dense, impermeable barrier. The result was a lining that was more than a seal. It was a symbiotic skin for the tunnel. It prevented life-giving water from seeping wastefully into the surrounding dry soil, and just as critically, it held back the earth itself, preventing catastrophic collapse that would bury workers and erase years of labor. This hidden, damp-setting chemistry was so effective that many qanats remain structurally sound and in use after 2,500 years. The durability of sarouj was never about glory. It was about silent, relentless service. It sustained entire civilizations like Persepolis, turning deserts into gardens from the inside out. This mixture represents a profound truth that some of humanity's most vital and durable innovations are the ones we never see, the hidden binders of survival that work in the dark to bring sustenance into the light. The hidden, damp-set mortar of the qanat worked in perfect stillness, but another ancient mixture found its purpose in relentless, violent motion. A Viking longship does not simply sail, it dances with the ocean, its timbers groaning as it rides over waves that would shatter a rigid hull. That dance was made possible by a substance as black as the deep sea itself, pine tar. This was not a casual waterproofing, it was a sophisticated, flexible skin engineered for survival. The process began not in a workshop but in a forest clearing with an earth-covered pit. Artisans would stack birch bark or pine roots, set a slow, smoldering fire, and capture the thick, pungent smoke and liquid that distilled out through a process called pyrolysis. The result was a viscous, complex brew of natural hydrocarbons and resins. Applied while still hot, this tar was poured and brushed into the overlapping seams between the ship's planks, a technique known as clinker construction. The heat drove the tar deep into the wood's pores, where it would solidify into a resilient, elastic seal. This was the genius of the mixture. It was not a brittle barrier. As the ship flexed and twisted in the North Atlantic swell, the tar flexed with it, maintaining a watertight bond where a rigid sealant would have cracked and failed immediately. Furthermore, the tar's chemical properties offered a subtle secondary defense. Its mild antiseptic nature helped inhibit the rot and marine organisms that would otherwise feast on the submerged wood. This organic concoction was as vital to the ship's integrity as the strength of its oak timbers. It transformed a collection of planks into a living, breathing extension of the sea itself. The tar's durability was not measured in centuries of immobility, but in countless leagues traveled under extreme stress. It enabled the lightweight, agile vessels that connected Scandinavia to Newfoundland, turning the ocean from a barrier into a highway. This mixture teaches a counterintuitive lesson that sometimes the most durable bond is not the stiffest one, but the one smart enough to bend without breaking, to move in harmony with the forces it must endure. The flexible seal of pine tar gave Viking ships their freedom on the open sea, but high in the Andes, a different philosophy of permanence was being carved from the bones of the mountains themselves. At Machu Picchu, the stones do not simply sit atop one another, they embrace. The joints between the massive granite blocks are so exquisitely precise that not even the blade of a knife can find a purchase. This is the pinnacle of Inca ashlar masonry, and its most fascinating mixture is arguably the absence of one. They built without mortar, creating durability through a negative space engineered to perfection. The technique relied on a concept of interlocking form. Each stone was painstakingly shaped using harder stones and abrasive sand, not to create flat surfaces but to craft unique, three-dimensional puzzles. The bottom face of one block would be carved with a subtle convexity, while the stone beneath would feature a matching concavity. When lowered into place, they would lock together, distributing weight not just downward, but laterally across the entire face of the joint. This created a monolithic stability where each block supported its neighbor in all directions. But how did they achieve such impossible precision with multi-ton stones? Recent research offers a compelling clue. It is possible the masons used a temporary slurry of wet clay or possibly even plant sap as a lubricant and a guide. They might have pressed a soft stone into a perfectly shaped socket, coating it with this muddy mixture, then transferred that impression to the next block to guide the carving. Once the fit was achieved, a good rain would simply wash the temporary paste away, leaving only the pure, intimate contact of stone upon stone. This method created a structure with a genius for seismic resilience. When an earthquake strikes, a rigid, mortared wall cracks and collapses, but an Inca wall, with its precisely engineered joints and slight flexibility, is designed to dance. The stones rumble and sway, settling and relocking into a new, equally stable configuration when the shaking stops. The mixture here was not a chemical paste, but a fusion of geometric intelligence and immense patient labor. It challenges our entire definition of a durable bond, suggesting that sometimes the strongest connection is not something you add, but a perfect void you meticulously create. It is durability born from subtraction, where resilience is woven into the very emptiness between things, proving that the most enduring structures can be held together by nothing more than a flawless fit. That perfect fit of stone in the Andes created walls that danced with earthquakes, but across the ocean, medieval architects sought to build walls of light. The soaring windows of Gothic cathedrals are a paradox of strength, vast expanses of colored glass that have withstood the gales and frosts of northern Europe for 800 years. This endurance is not a happy accident. It is the direct result of the glass itself being a meticulously crafted, durable mixture. Medieval glassmakers began with silica sand, but their flux was not soda ash, it was potash derived from the ashes of burnt hardwood. This gave the glass a different chemical personality, slightly less stable but with a unique character. To this base of sand and potash, they added lime as a stabilizer, and then the magic metallic powders. Cobalt oxide yielded a deep, celestial blue, copper created a fiery ruby red, and manganese produced regal shades of violet. This molten cocktail was not poured into perfect molds. It was gathered on the end of a blowpipe, blown into a cylinder, cut open, and flattened into sheets. This primitive process created glass that was inherently uneven, full of subtle waves, bubbles, and variations in thickness. A pane was often thicker at one end, a feature called crown glass culling, a frozen record of the molten flow. These imperfections, far from being flaws, are central to the glass's legendary durability. The chemical composition, rich in potassium from the potash, actually makes medieval glass more resistant to the specific type of corrosion that attacks modern glass. Environmental moisture interacts with the surface to form a stable, protective patina that slows further degradation. The uneven thickness also scatters light in a living, dynamic way, meaning the windows don't just transmit light, they animate it, turning a beam of sun into 1,000 points of dancing color. Furthermore, the very process of spinning and flattening the glass created internal stresses that, counterintuitively, make it more resilient to thermal shock and physical impact than uniformly flat, modern glass. Each diamond-shaped quarry or majestic figure is not a fragile picture in a lead frame. It is a structural element in its own right, a piece of engineered stone made from light and metal and fire. The durability of this mixture granted these buildings their soul, allowing faith to be written not in perishable paint, but in eternal, illuminated color that has outlasted kingdoms. That eternal, illuminated color of stained glass transformed light into a spiritual language. Yet for the monumental domes and needle-like minarets of Ottoman Istanbul, a different kind of alchemy was needed, one that could armor stone and brick against the harsh realities of wind, rain, and time. Their solution was a fired skin of radiant color, the terracotta cladding tile. This was not mere decoration applied as an afterthought, it was an integral, engineered shield. The process began with a specific selection of clay bodies, chosen for their plasticity and mineral content. This clay was meticulously mixed with water and fine sand, a temper that prevented excessive shrinkage and cracking during the drying and firing stages. Artisans would then shape the tiles, often into complex geometric patterns, before applying the most crucial layer, a thin slurry called a slip. This slip was a quartz-rich mixture, a fine paste of silica that would become the tile's true face. The shaped tiles were then loaded into kilns for a long, controlled firing at intensely high temperatures. This was where the transformation occurred. The heat did not just harden the clay, it performed a precise act of vitrification on the quartz-rich slip. The silica particles at the surface began to fuse together, melting just enough to form a continuous, glass-like glaze that was chemically bonded to the clay body beneath. This created an impermeable ceramic skin. The practical benefits were immense. This vitrified surface was completely waterproof, shedding rain and snow that would otherwise seep into the porous brickwork, freeze, expand, and slowly explode the masonry from within. It was resistant to the soot and pollution of a thriving city. Its colors locked into the glassy matrix, refusing to fade under centuries of sun. And it was incredibly hard, resisting abrasion from wind-blown sand and debris. The iconic blue of the Sultan Ahmed Mosque, the emerald green of slender minarets, these were not paints that could peel, they were minerals transformed into permanent stone glass. This mixture demonstrates a profound understanding of material potential. The Ottomans took one of the humblest building materials on earth, clay, and through the controlled application of elemental fire, elevated it into a radiant, protective armor. It was a technology that served both the soul and the structure, creating a skyline that gleamed with spiritual symbolism, while its very brilliance was a ruthlessly practical guarantee of endurance. The radiant, vitrified skin of Ottoman tiles repelled water with a glassy hardness, but in the arid landscapes of the American Southwest, durability required a completely different philosophy. Here, the very earth itself was coaxed into becoming shelter. The ancient pueblos that rise from the desert mesas are monuments to Adobe, a mixture of profound simplicity and hidden sophistication. At its core, Adobe is just earth, water, and straw mixed into bricks and dried in the sun. Yet to survive for centuries in an environment of scorching days, freezing nights, and the rare but catastrophic deluge, these builders incorporated subtle stabilizers, turning a basic recipe into a resilient technology. They understood that the local clay alone could be brittle. To fortify it, they would sometimes mix in natural asphalt seeped from tar pits, a sticky, waterproofing binder that repelled moisture. In other communities, plant resins or even animal blood were used as organic binders, adding cohesion and reducing the tiny cracks that form as the mud dries and shrinks. These additives were not arbitrary, they were a direct response to the land's offerings and challenges. The result was a brick with improved tensile strength and water resistance, capable of withstanding the infrequent but torrential rains that could otherwise melt a simple mud wall back into the earth. But the genius of this mixture extended beyond the brick itself. The massive thermal mass of these thick adobe walls created a natural climate control system, absorbing the desert's heat during the day and slowly releasing it through the cool night, making the interiors livable through extreme temperature swings. This building practice was never just construction. It was a cultural ritual, a communal activity where knowledge of the right soils, the right stabilizers, and the right building seasons was passed down through generations. The mixture was a dialogue with place, using exactly what was underfoot to create homes that were not imposed upon the landscape, but grew from it. Their endurance is a quiet testament to a localized wisdom, where durability was achieved not by conquering nature with imported materials, but by listening to it and strengthening its own inherent potential. The thick, sun-baked walls of an adobe pueblo create shelter from the elements, but for a city of 1 million people, survival demanded a different kind of conduit. To bring life into the heart of ancient Rome, engineers turned to a metal both miraculous and malevolent, lead. Their vast network of water pipes, known as fistulae, was a triumph of urban engineering built upon a material we now understand carries a hidden toll. The mixture itself was deceptively simple, nearly pure lead, smelted from ore and cast into flat sheets. These sheets were then rolled around a cylindrical form, and the seam was sealed with a solder made from a lead and tin alloy, creating a continuous, watertight tube. This choice was not made out of ignorance of other options. Clay pipes and even hollowed stone were known, but for very practical reasons of performance and scale. Lead was incredibly malleable, allowing it to be easily shaped and bent to navigate the complex underbelly of a growing city. Once installed, it was virtually impermeable, eliminating the constant losses from seepage that would plague earthenware conduits. And perhaps most importantly for the Romans, it was durable in a way that mattered for infrastructure. It would not crack from ground settlement or root intrusion, and it resisted corrosion from the soil itself. This last point holds a fascinating, accidental chemistry. The water flowing from the aqueducts into these pipes was not pure. It was what we call hard water, rich in dissolved minerals like calcium carbonate. Over time, this mineral-rich water reacted with the inner surface of the lead pipe, depositing a thin, stable layer of insoluble scale. This scale, primarily composed of minerals like cerussite and hydroxyzite, actually formed a protective barrier between the water and the raw lead, significantly reducing the metals leaching into the supply. It was an unintentional self-protecting lining, a built-up crust that made the pipe more inert the longer it was in service. The result was a hydraulic network of astonishing longevity and reliability, a system so robust that sections of these fistulae have been found intact after 2 millennia buried in the earth. This mixture enabled an urban lifestyle of public baths, fountains, and private latrines on a scale unmatched until the modern era. The legacy of Roman lead pipe is a complex one, a stark lesson in material science where a choice made for impeccable engineering reasons, prioritizing impermeability, malleability, and ease of installation on a colossal scale, came with a long-term human cost that remained invisible for centuries. It stands as a sobering reminder that durability in a material is only one part of the equation, and that the most enduring systems are those that strengthen the structure without weakening the people within it. The enduring legacy of Roman lead pipe reminds us that material choices are never simple equations. But what if durability could be grown, harvested from a living tree and built up, layer by patient layer, into an armor both delicate and nearly indestructible? This is the story of Chinese lacquerware, a 15th mixture where resilience was not forged in fire, but cultivated in stillness. The process began with a precise, almost ritualistic cut into the bark of the Toxicodendron vernicifluum tree, the lacquer tree, to collect its raw, milky sap. In its natural state, this sap is a potent substance that can cause skin reactions, a fact ancient artisans respected with great care. Once collected, the raw lacquer was meticulously filtered and often mixed with mineral pigments, iron oxide for deep blacks and cinnabar for vibrant reds being the most iconic. Then began a feat of patience that defies modern sensibilities. A base object, perhaps a wooden bowl or a fabric form, would receive its first whisper-thin coat. It would then be placed in a special curing chamber with precisely controlled humidity and temperature. The lacquer does not dry by evaporation, but through a complex enzymatic reaction with moisture in the air, a process that polymerizes the urushiol molecules in the sap, transforming the liquid into a hard, stable layer. Only when that layer was fully cured would the next be applied. Masters repeated this cycle dozens, even hundreds of times over months or years. The result was not a thick shell, but a laminated composite material of extraordinary properties. Each microscopically thin layer bonded chemically to the last, creating a unified whole that was far stronger than its individual parts. This organic polymer shield became impervious to water, highly resistant to heat and mild acids, and incredibly resilient to scratches and wear. It created objects like the exquisite boxes and trays from the Han Dynasty, which today, over 2 millennia later, retain a deep, mirror-like gloss and structural integrity that modern plastics cannot rival. This mixture represents a philosophy of durability built through accumulation and perfect environmental control. It was an act of collaboration with the chemistry of a tree and the very air itself, proving that true toughness can be a slow, deliberate art where time itself is the most crucial ingredient in the recipe. That cultivated, organic armor of lacquer was a triumph of patient chemistry, but another ancient mixture sought to create a color so perfect it had to be invented from scratch. On the walls of a pharaoh's tomb, a particular shade of blue does not whisper of the sky, it declares it with the confidence of stone. This is Egyptian blue, and it holds the distinction of being humanity's first fully synthetic pigment. Its creation was an act of deliberate, high-temperature alchemy. Artisans would combine 4 mundane ingredients: quartz sand for silica, a copper mineral like malachite, crushed limestone for calcium carbonate, and a source of alkali, often the same natron used in faience. This dry powder was placed in a ceramic crucible and heated in a kiln to a blistering 900 degrees Celsius. At that precise temperature, the components fused, undergoing a solid-state reaction that grew tiny, brilliant crystals of calcium-copper silicate. Once cooled, this blue cake was ground into a fine powder, ready to be mixed with a binder and applied. The significance of this mixture goes far beyond its beauty. While organic blues from plants like woad or indigo are notorious for fading under light, Egyptian blue is phenomenally stable. Its color is locked into the very crystal structure of the synthetic mineral, making it resistant to sunlight, moisture, and chemical changes that would cause other pigments to degrade into ghosts on the wall. This incredible durability has granted it a second, unexpected life in modern archaeology. Scientists can now use a simple infrared light source in a dark room. When shined on an artifact, even one where the blue appears faded or obscured by grime, Egyptian blue will luminesce with a bright, unmistakable glow, revealing brushstrokes, repairs, and artistic techniques invisible to the naked eye. Furthermore, because the recipe was so specific and complex, its presence on an object far from Egypt acts as a permanent chemical fingerprint, tracing ancient trade routes of materials and ideas across the Mediterranean world. This pigment was more than a color, it was a captured idea of the celestial, manufactured to last for eternity. Its persistence today is a silent conversation across millennia, where the original desire for an undying blue now helps us see the invisible hand of the ancient artist, proving that sometimes the most durable legacy a culture can leave is not just what it built, but the very light it chose to trap in stone. That synthetic blue pigment was a triumph of controlled fire, but in the floodplains of West Africa, builders discovered a stone that cured itself under the open sky. The Great Mosque of Djenné rises from the earth like a colossal termite mound, its towering spires and unique buttresses all sculpted from a single, remarkable material, laterite. This is not a stone quarried from a mountain, but an earth harvested from the ground beneath their feet, a mixture that holds its transformation within. Laterite is a deep, reddish soil, rich in iron and aluminum oxides, formed over millennia by the intense tropical weathering of bedrock. In its natural, waterlogged state, it is soft, almost clay-like, and can be cut with simple tools into large, heavy blocks. This was the moment of opportunity for the masons of the Mali Empire. They would quarry these blocks during the dry season, when the earth was firm enough to hold shape, carving them with relative ease into the forms needed for the mosque's ambitious architecture. Then they left the blocks to bake in the fierce sun. This exposure was the catalyst for a silent, geochemical miracle. As the moisture evaporated, the iron oxides within the laterite underwent a process of hydration and crystallization. Essentially, the iron rusted, but in a controlled, constructive way, binding the loose particles of clay and silt into a solid, stony matrix. The block didn't just dry out, it petrified, transforming from a malleable earth into a hardened, durable brick. This self-curing process created a building material perfectly adapted to its environment. The hardened laterite was highly resistant to the intense erosion from seasonal rains that would wash away ordinary mud brick. Its density and mineral composition also provided excellent thermal mass, helping to moderate the interior temperature of the mosque against the equatorial heat. The entire construction cycle was a dance with natural chemistry. Builders had to understand the timing, quarrying the material when it was workable, then allowing nature the precise period it needed to perform its strengthening act. The result is a structure that appears to have grown from the landscape itself, its color blending with the very earth it stands upon. This mixture represents a profound philosophical approach to building, one of patient collaboration. There was no kiln, no complex mortar, no imported stone. There was only a deep reading of the land's own potential, an understanding that the most durable foundation could be a material that was willing, with a little air and time, to turn itself into stone. The self-petrifying stone of Djenné grew strong under the open sky, but in the dim, vaulted ceilings of northern Europe, medieval masons faced a different architectural dream, one of impossible height and light. To achieve it, they began a quiet, revolutionary experiment in material partnership. In the soaring ribs of a Gothic cathedral, you can sometimes find the ghost of a forgotten metal, an iron bar or a flat, blackened cramp set deep within the stonework. This is not a later repair, but an original, ingenious component of the design. The mixture here was not a paste or a glaze, but a structural hybrid, a deliberate marriage of stone and iron. Each material was tasked with what it did best. The limestone blocks, meticulously carved and stacked, were masters of compression, bearing the immense downward weight of the vault. But stone is brittle. It has almost no strength when pulled or bent, a property called tensile weakness. This is where the iron entered the recipe. Forged into rods, bands, and U-shaped cramps, these metal elements were embedded at critical points, often at the peak of an arch or tying together the delicate stone ribs of a ceiling. Their job was to handle the tension, the invisible pulling forces that threatened to make the slender pillars buckle or the wide vault spread apart and collapse. This composite system was a stroke of intuitive engineering genius. By letting iron silently shoulder the tensile stresses, the masons could dramatically reduce the bulk of the supporting stone. This is what allowed for those breathtaking vertical leaps, the forests of slender columns, and most importantly, the vast walls of stained glass that defined the Gothic quest for luminous transcendence. The entire building became a skeletal frame with stone for bones and iron for sinew. Yet this innovation came with a hidden, long-term vulnerability, the very enemy that the iron pillar of Delhi had somehow defied: corrosion. When the embedded iron rusted, it expanded with tremendous force, a slow, relentless pressure from within. This expansion could and did crack the surrounding stone from the inside out, like a seed sprouting in concrete. The medieval builders, through hard-won observation, recognized this threat. Their response was an empirical move toward protection. They would sometimes coat the iron in a layer of molten lead, or paint it with pitch or tar before setting it in place, crude but thoughtful attempts to create a barrier against moisture. These early, pragmatic coatings were the first steps on a path that would lead, centuries later, to the galvanized rebar of modern reinforced concrete. The iron in those vaults was more than a hidden support, it was a conceptual bridge. It showcased a dawning understanding that the future of durable, ambitious structures did not lie in finding one perfect material, but in creatively combining the strengths of two, a principle that now holds up our entire modern world. The iron sinews within a Gothic vault were a hidden compromise, a material marriage for the sake of ambition. Yet for the master metalsmiths of the ancient Americas, the goal was not to hide strength, but to weave it directly into the very soul of an object. The magnificent gold artifacts that emerged from cultures like the Muisca of Colombia or the Moche of Peru hold a secret in their gleam. They were rarely made of pure gold. Instead, they were crafted from a deliberate, sophisticated alloy known as tumbaga, a mixture of gold with significant amounts of copper and sometimes silver. This was not a sign of scarcity or deception, but a profound understanding of material science applied to spiritual need. Pure gold is famously malleable, so soft it can be molded by hand. For a ceremonial object meant to be passed down through generations, handled in rituals, and exposed to the elements, this softness was a liability. The addition of copper transformed the metal on a fundamental level. It lowered the melting point, making it easier to cast into intricate forms using the lost wax technique. It changed the color, giving the finished piece a distinctive, warm, reddish hue. Most importantly, the copper atoms interspersed within the gold crystal structure created a harder, more durable alloy. This was a metal engineered for permanence, one that could resist dents, scratches, and deformation far better than its pure counterpart. But the artisans did not stop there. They possessed a finishing technique of breathtaking ingenuity called depletion gilding. After casting the tumbaga object, they would apply a paste of corrosive natural salts and then carefully heat it. This process would selectively dissolve the copper from the very surface layer, leaving behind a thin, porous skin of nearly pure gold. This layer was then burnished to a high sheen, creating a brilliant, luxurious finish that masked the tougher alloy beneath. The result was an object of perfect duality, a hard, resilient core cloaked in an untarnishable, sacred radiance. This mixture served a purpose beyond the physical. It ensured that a ceremonial mask, a ritual breastplate, or an offering meant for the gods could endure the touch of countless hands and the passage of uncounted years without losing its divine luster. The durability of Tumbaga was not merely technical, it was ritualistic. It was a guarantee that the connection to the eternal, symbolized by the sun like gold, would remain physically intact for as long as the community itself endured. In these artifacts, material science and spiritual belief were fused as completely as the copper and gold in the alloy itself, creating a legacy where resilience was not just a property of the metal, but a sacred promise made solid. The sacred golden promise of Tumbaga was designed to endure above ground, but another metal alloy mastered the art of survival in the dark. The few surviving large-scale bronze statues from antiquity, like the Rias warriors discovered in the sea off Italy, are not merely relics, they are miracles of metallurgical precision. These figures, emerging from the earth or the seabed with their power undimmed, owe their existence to a recipe as calculated as any architectural mortar. The typical mixture was around 90% copper to 10% tin, a proportion that struck a perfect balance. Copper provided the base, but pure copper is too soft for a towering figure meant to stand for centuries. The addition of tin transformed it, creating a true bronze alloy that was significantly stronger, harder, and far more suitable for the complex lost wax casting process that gave these statues their lifelike detail. Yet the ancient foundry masters did not stop there. To ensure the molten metal flowed perfectly into every crevice of the mold, capturing the subtle tension of a muscle or the fold of a cloak, they would often introduce a small, deliberate impurity, about 1 or 2% lead. This addition improved the fluidity of the alloy, allowing it to fill the most intricate negative spaces before it cooled and solidified. The result was a cast of breathtaking fidelity. After cooling, the statue's surface was often further enhanced through inlay, with lips of copper, nipples of a different alloy, or eyes of ivory and glass adding startling realism. But the true test was time. This specific bronze mixture, when kept polished and maintained in its original context, developed a stable, protective patina that shielded the underlying metal. However, the ultimate reason we have any of these statues at all is a story of loss leading to preservation. Countless thousands of bronze sculptures that stood in city squares and temples were eventually melted down for their valuable metal to make coins or weapons in later eras. The Rias warriors and others like them only survived because they were lost, submerged in a shipwreck or buried in a stable, anoxic environment that arrested the corrosion process. Their durability is thus a layered phenomenon, a combination of a perfectly engineered alloy, capable of being cast into sublime art, and the sheer accident of being forgotten in a protective tomb of mud or salt water. They represent a poignant truth that sometimes the materials engineered for public immortality only achieve it through disappearance, preserving a flash of artistic genius not in the light, but in the forgiving dark. The rust-defying iron of Delhi and the self-healing harbors of Rome are not isolated wonders, but points on a global tapestry of innovation. From the rice mortar of the Great Wall to the breathable stucco of the Maya, each of these 20 mixtures reveals a universal truth about ancient ingenuity. It was born from a deep, patient conversation with the local world, a dialogue of necessity and acute observation. These builders did not seek to conquer their environment with imported materials, but to listen to it, to understand the potential hidden in their own volcanic ash, their local clays, their harvested grains, and even their discarded pottery. The lesson they leave for us is profound. True durability is not merely a measure of brute strength or resistance. It is a quality of harmony, a sophisticated alignment with chemistry, climate, and the character of locally available resources. These ancient material scientists, working without formal laboratories, mastered the art of collaborating with nature's own toolkit. They engineered materials that invited seawater to strengthen them, that used atmospheric moisture to cure, that turned waste into waterproof binders, and that grew stronger through the very processes we now spend billions to prevent. Their results continue to baffle and inspire our modern engineering, not because they possessed secret knowledge we have lost, but because they approached the problem from a fundamentally different perspective. As we now face monumental challenges in building a sustainable future, with concerns over carbon emissions and resource depletion, perhaps the path forward requires looking back. The answers to resilient, enduring construction may not always lie in inventing new, complex polymers in a lab. They might be waiting in the rediscovery of these time-tested alchemies, in revisiting the wisdom of working with the grain of the natural world rather than against it. Imagine what we could build by combining their philosophy of harmony with our understanding of material science. Which of these forgotten mixtures do you think holds the most promise for our future? Share your thoughts in the comments below and subscribe to continue unraveling history's greatest mysteries with us.